Welcome back, class. Today we're going to be working more with series, and today we're even going to see how a series can even develop into something a little bit more. As we go further and further along a series, we'll start to discover something called a limit. Okay, so let's go ahead and first take a look at number 1 here. When we start working, when you start working, you earn $25,000. If salaries annually increase by 5%, how many years will it take to earn a total of $1 million? And we want to find out what our annual salary will be at that time. Well, if we think about what's going on here, we first start off with $25,000. And then the next year, we're going to earn 5% of that. What exactly is 5% of that? Well, based on what you did in Algebra 2, you know that you're going to have the $25,000, 100% of that plus an additional 5%. So you're going to earn 1.05 times 25,000. That'll be your salary in year 1. So this right here is in year 1. Okay. In year 0, your first year, this is kind of what you start here. In year 0, this is where you kind of begin. And so you can see here that what we're doing is we're basically saying you take the initial amount and you're going to be multiplying that by 1.05 to get your next year's salary. Now don't forget that you're earning this income, so you don't just have 25,000 times 1.05. You have $25,000 from the very first year, your starting year, and then you add on the next year 25,000 times 1.05. So you're actually going to earn a lot more, right? You're going to earn like 50,000-ish, right? So then we keep this going, and in the next year, you're going to earn 25,000, and then times 1.05. That was the amount you had in year 1, but then you're going to have that salary, and you're going to earn 1.05 of that as well. Or basically, you're saying you have 1.05 squared. Okay, and so this is occurring in year 2 now, right? So 1 year has passed. Now another year has passed. You're going to multiply by another 1.05. And you just keep this procedure going, right? We add on another 25,000 times 1.05. And this time it's going to, since you're multiplying another 1.05, you now have 1.05 to the third. And you keep going and going and going. So you have plus 25,000 times, it's like dot, dot, dot in there, and you have 1.05 to the power of something, right? It's to some n power. So we basically have this series where we created this long expression here. And how do we create this expression? Well, notice that every single time we're multiplying by 1.05. Hopefully you're starting to think, well, what is this? Is this an arithmetic or is it a geometric series? Well, since we're multiplying, we know it's going to be a geometric series. And because it's geometric, we know we have our formula, right? Geometric series. Basically, the sum of our terms is going to equal the first term times 1 minus r to the n power all over 1 minus r. And so if we plug in our values, we're saying, what's the initial value? We're starting off with $25,000. 25,000 times 1 minus, what is our rate? What are we, our common ratio, right? What's our common ratio? It looks like we're always multiplying by the value of 1.05 every time. So we have 1 minus 1.05 to the n power over 1 minus 1.05. And that's equal to S of n. Okay. Now, the question is asking us, how many years will it take to earn a total of $1 million? What does it mean when it asks us how many years? What are we looking for? Hopefully what you're saying is how many years is, this is the same thing as solving for n, which means we must know what's on the other side. How many years will it take to earn a total of $1 million? Oh, $1 million. That's going to be our sum, right? When we add everything up, it should add up to $1 million. So now our equation looks like this, and now all we need to do is solve for that n value. Okay, so I'll just do a little bit of algebra here and solve for our n value. So it looks like what we have to do is take 1 million and then divide it by 25,000 And obviously we do get 40 there, right? So we're going to get 40 equals 1 minus 1.05 to the n over 1 minus 1.05. I'm then going to take my 40 and multiply it by 1 minus 1.05. So I'm just going to take my answer and multiply it by 1 minus 1.05. And then I'm going to take that answer, which is negative 2, which equals 1 minus 1.05 to the n. Looks like we need to subtract 1 now, right? So we're going to get negative 3. So answer minus 1, we're going to get negative 3. And then we're going to take that answer, and negative 3 equals negative 1.05 to the n. And then now the negatives, that's really minus 1.05 to the n like that, right? So what we can do is actually divide out that negative. So we're going to get positive 3. So negative answer, that'll give us positive 3. And then now we are coming across a situation where we have 3 equals 1.05 to the n. How do we solve for n? Hopefully what you're saying is you're logging both sides, right? So we log both sides, and then we can bring that exponent down like this. And then now at this point we want to solve for n, so we divide both sides by log of 1.05. So I'm going to take log of my answer, log of 3, and then take that value and divide it by log, and feel free to do this in your own scientific calculator as well, log of 1.05. And we get an answer of 22.52 basically, okay? So it's going to take us about 22.52 years. Now, how do you round, right? Well, if you're getting an annual salary, is 22 years going to cut it? 22 years is running a little bit short. You're not going to reach that $1 million just yet. So you actually have to round this value up. So you're actually going to say it's going to take you about 23 years. You need to surpass the $1 million mark to actually make $1 million. Okay? All right, so what would your annual salary be at that time? Well, now that we have the n value, the 23, we can just plug that in, right, and see what our annual salary is. We can just say 25,000 times 1.05 to the 23rd power. And that'll give us an annual salary of $76,788 basically is your annual salary. Okay, so those are going to be your two answers for number 1. Sorry, I'm running a little short on space here, so I'm actually going to erase. Maybe I don't have to erase. Let's see what happens. If I end up finding that I do need more space, I will erase this answer. So feel free to rewind the video if you need to. All right, now let's take a look at limits. The idea of limits is basically saying as our value gets larger and larger, what are we essentially going to? That's kind of like what we were doing in the first problem. As we kept getting larger and larger salaries, what was the value ending up going to? Well, look, we ended up getting to $1 million. Okay, let's see what happens here. Now we have this equation, f of n equals half to the n power, and we're going to just plug this into our calculator and just see what we get. Go ahead and use your own scientific calculator as well, and plug in, half to the power of, half to the power of 1, we know that's just half, right? Let's just do half to, or actually let me write this as a decimal, 0.5. And then we're going to make it half to the power of 10 now, okay? And now we're going to get a value of 9.76 times 10 to the power of negative 4, basically, okay? And then as we keep on going, we're going to make this go to the 100th power now. And then we're going to get 7.88 times 10 to the power of negative 31. Wow. Are these numbers getting bigger or smaller? That's for you to judge. Now let's go to the 1000th power. And we get 9.33 times 10 to the negative 302. Okay. And you know what? If you're doing this on your own scientific calculator, you may be getting a different result than me. Try it out. See what you get. But I think by the time we get to the 0.5 to the 10,000, we should basically all be in agreement that our calculator is giving us a value of 0. 0? How's that possible? This should not work. Maybe your calculator even says like domain out of bounds or something like that, domain error, right? This is actually a value where it's not really working out for us. We know that 0.5 to the 10,000 actually doesn't give us 0, but as you can see from our table, our number is getting smaller and smaller and smaller, but it's basically getting really, really, really close to 0. That's what it means to find a limit. A limit says as your number gets larger and larger, what is the value of your expression getting to? It's getting closer and closer, in this case, to the value of 0. Okay, let's take a look at what this looks like graphically. Okay, now we did have our table already written out right there, so I'm not going to go ahead and just rewrite everything, but just know that what we're doing is we're saying that now the n value represents x and the y value represents f of n. Okay, so that's your x and y table basically. Okay, so as we go ahead and graph this, let's make a coordinate plane. We have the value at, at 1. We're going to have the value at half, 1. We're going to have a value at half. At 10, so 10's like way over here, right? 10's really small. And then 100 is really, really small, right? Our number just gets smaller and smaller and smaller. Well, can you imagine what happens as your number actually goes the other way? Maybe we plug in 0. What happens when you plug in half to the power of 0? Oh, that's, what's that? That's 1, right? Anything to 0 power is 1. So 0 will give us 1. What happens if we backtrack? Let's say we plug in negative 1. Let's see, half to the negative 1, that means it will do its reciprocal. So half to the power of negative 1 will give us a value at 2, right? So this number is going to get a little bit higher at 2, okay? As we go a little bit more, let's just say, I don't know, let's just do like negative 100, right? Let's go way over on this side, negative 100. Well, then they're taking the reciprocal of this. You're really saying 2 to the 100th power. Oh my gosh, that's a really large number, right? So negative 100 is going to take us way, way up here. So what you see is you create this graph that is an exponential decay problem, like this, right? And so what we're noticing here is we're just graphing an exponential decay. We know it's decay because it's half, right? That rate is smaller than 1, so we see it's exponential decay. Now the new part to this is now taking into consideration what we call the limit. Notice what this says. The way that we say this is this, let me write this down actually. This reads as the limit as x, or let me rewrite that. The limit of half to the power of n as x, or not x, but n approaches infinity. The limit as half to the power of n as n, this should be an n, as n approaches infinity. That's what it means. Notice the arrows. N is going to infinity. Okay? As n is going to infinity is what's happening. As x goes to infinity, where are you going? This value of the exponential is getting closer and closer to our y-axis of 0 is 0. That's how we read this. So we say the limit of half to the n as n approaches infinity is actually the value of 0. Okay? Because it's going to 0, what we say is that this limit exists. The limit exists. And the limit is 0. Okay? So that's going to be our new part to series, that as we add numbers up more and more and more, we're saying, what is that number going to? In this case, we're going closer and closer to 0, and so our limit is 0 as n goes to infinity, like that. Okay? All right, let's go on to the next page. Let's take a look a little bit more, look a little bit more at limits in terms of the functions. All right, so draw the graph of f of x equals negative half x plus 2. Let's go ahead and draw that. Okay, so we take a coordinate plane here. We know we have a y-intercept at 2. We have a slope of negative half, so down 1 over 2, down 1 over 2. Okay, and then let's just go one more actually. Down 1 and over 2, like that. Okay, and then I'm just going to go ahead and draw a line here. There we go. All right, so there's negative half x. Whoops, that's off, isn't it? You get the idea. All right, so negative half x plus 2. What does the graph go to when x goes to 5? Okay, so this question is asking what it goes to, not what it is, but what it's going to. And when we say what is it going to, what we're referring to is the idea of limits. Okay, so as this graph is going to 5, well, 5 is right here. What is it going to? That means as, I'll do this in a different color, as our line goes from the left, what we're going to now say is we're coming from the left. The way that we can say this in mathematical terms is what we're going to write is we're going to take the limit as x goes to 5 from the left. The way we say from the left is you do, I'm going to write this big here, is write a 5 with a superscript with a negative sign. A negative means you're coming from the left-hand side. If you have a superscript that's a positive, it's saying you're coming from the right. So this is from the left, and this is from the right, okay? And I'm going to erase this because I just realized I'm writing way too big here, okay? But I just want you to see that if you have a superscript that's negative, it's from the left, and a positive means you're coming from the right, okay? So let's go ahead and rewrite this. From the left means limit as x goes to 5 from the left of our equation of negative half x plus 2. That's what we want to say. Okay? And what is it going to? As you're going to 5 from the left, you're going closer and closer to 5. What are you going to? You're getting really close to this value here. What is that value? That value is actually at negative half, right? So the limit as x goes to 5 from the left is negative half. So the limit as x goes to 5 from the left of our function is going to negative half. Well, it's not enough to just say where it's going from the left. What you also want to do is come in from the right. So we want to see as we're going in from the right side, where are we going? And the way we write that is, from the right side, what we can say is limit as x goes to 5 from the right of our function negative half x plus 2, like that. What's it going to? As you come in from the right, you're going to the value of, it's the same value. You're coming to that same value of negative half. So it's also equal to the same value as limit as x goes to 5 from the right of f of x. Okay? So as it turns out, the limit as x goes to 5 from the left is the same as the limit as x goes to 5 from the right, and they're both the value of negative half. And therefore, when you find that the limit as x goes to 5 from the left is the same as the limit as x goes to 5 from the right, then what we can say is this creates a whole new limit expression saying limit as x goes to 5, just 5. What it means if you don't have a superscript there is it's coming from the left and the right. It's going to the same amount. It's going to the value of negative half, like that. So limit as x goes to 5 from the left and right is negative half. Okay? All right, let's go on to C. The limit as x goes to infinity. Even though these are very small, you got to pay special close attention to where you're going to. As you're going to infinity of this line, let's see what happens. As you go to infinity, I'm going to do this in a different color now. Let's do green. Okay, so we take the same line, negative half x plus 2, but we're going to infinity, meaning infinity is which way? Infinity is this way. So as we go this way, where are we going? That line is going further and further down, right? It keeps going down and down and down and down. So because it keeps going down and down and down and down and down, this is going to the value of negative infinity, like that. Okay. This concept, it can be tricky. It's a little confusing. So please stop, rewind if you need to, rewatch it, And if it's still not making sense, hopefully our Zoom discussion this week will help. Okay? Let's keep on going. Number 4 here. Y equals 1 over x for x greater than 0. Do you remember what that looks like? That rational function? We had done that rational function before, right? Rational functions look like this. And because technically it says for x greater than 0, technically we don't have this piece, but you do know that there is another part of the function that actually goes in quadrant 3, right? All right, but we do see that it's x is greater than 0, so we don't want to be concerned about the quadrant 3, so that's why I made it a dotted line, okay? All right, let's go ahead and address the questions that we see here. Find the limit as x goes to 0 of 1 over x. Now, because this says x goes to 0, remember what this means. This means you're coming from the left, and also from the right. However, because this particular scenario had a restriction, x is greater than 0, there was nothing coming from the left side anyway. So we don't need to be concerned about anything from the left. All we're concerned about is as we go to the right. So as you go to the right, as you go from the right rather, as you go from the right, what is your value of y going to? Notice how it gets higher and higher and higher, and it's going to keep going to infinity. Okay? How can we test that theory out? Well, look at this table that you see down below. Okay? If you start off at 1, and then you go to half, and then you go to fourth, and then you go to a tenth, and then a thousandth, right? You're getting smaller and smaller and smaller. Let's see what happens as we make those numbers get smaller. So we're going to go ahead and plug some numbers in. We have 1 divided by, well, 1 divided by 1 we know is 1. 1 divided by half is 2. 1 divided by 1/4 is 4. And then 10. And then 100. And then 1,000. These numbers are getting larger and larger and larger, right? So they get bigger and bigger and bigger. So because they get bigger, we know that this is basically going to the value of infinity. Okay? All right, let's go on to the next one. Find the limit as x is now going to infinity. So now you're going the other way. Okay, so you can take a look at what's happening along the graph, but let's verify that with our table. As our number gets larger and larger and larger, you're going to get 1 over 100, 1 over 1,000, 1 over 1,000,000, right? Look at that. What's happening to these numbers? Hopefully you're starting to see that these are getting smaller and smaller and smaller. What's it getting to? What's it getting close to? Not what it equals, but what is it getting closer to? It's getting closer to the value of 0 because, as you know, that's where the asymptote occurs. So you're getting really, really close to 0, never quite touching it, but it just keeps getting closer and closer. That's what it means to find the limit. What is it getting closer to? Not what is the actual value. Okay? So we took a look at how we can see limits graphically. What I would also like to show you is how to find a limit algebraically. Okay? Now to find a limit algebraically, there's this definition here. As n goes to infinity, if a sequence or function has a finite limit, meaning it has a number, it truly equals something, then we say it is convergent, or it converges to that value of L. Okay? If a sequence or function that doesn't have a finite limit, then we call that divergent. If a sequence that doesn't have a finite limit is divergent. If we see that it goes to infinity, or if it goes to negative infinity, or maybe it's actually going back and forth. Maybe you have a value on your graph, you have a value here and here and here. Think of like a sinusoidal curve, right? If it's like this, it keeps going back and forth. Then you really can't pinpoint as x goes to infinity that you're really going to have a value because it just keeps going up and down, up and down. In that case, you say that it is divergent. So we have two different scenarios, convergent and divergent. Okay? Now, in order to find our limits, what we can do is a three-step process. I'm going to write down those steps. Actually, where do I have room? I'll write it down up here. Okay? So, what we want to do, the process is step 1, you're going to divide each term by the highest power of the value of n in the denominator. Okay? The second step is what you're then going to do is you're going to simplify everything. And then the third thing you're going to do is you then can take the limit. You can evaluate as n is going to infinity. Okay, now one thing you want to remember, I'll put this in red to make this important. You got to remember this part here, that you need to write the limit as n is going to infinity every single time at each step. Okay? Until you evaluate it. Until you evaluate it. Okay? So keep that in mind as we do these problems. Let's take a look at number 5 and do that 3-step process. So we have limit as x goes to infinity of 2n minus 6 over n plus 10. This is not quite as easy a problem as, say, 1 over x, where we knew what that graph looked like, right? It's not as simple as a linear equation where we know that this is what it looks like. This time we have some weird rational expression, and I don't know what it's going to. So what I can do is this algebraic process. If something gets too difficult, we can always solve something algebraically to make our lives easier. Okay? You could also make a table and just do what we did last time, which is plug in bigger and bigger and bigger numbers, or you can just solve this algebraically. So let's first take a look here. Step 1, divide each term by the highest power of n in the denominator. Look at n. What's the highest power? The highest power is a degree of 1. So what we're going to do is we're going to take every single term and divide it by n to the first. So that means 2n divided by n to the first minus 6 divided by n to the first all over n divided by n to the first plus 10 divided by n to the first. Notice how I took every single term and divided it by n to the first power. Also keep in mind the thing I made in red here. Write the limit as n is going to infinity, because we are not actually solving this problem. A limit is different from solving an equation. What we're seeing is what it's going to, not what it's actually equal to. Okay, so we just want to see what you're approaching. So now what we can do is simplify this problem here. Now notice, n divided by n, those just cancel out, right? N divided by n cancel out. So what we're left with then is 2 minus 6 over n divided by 1 plus 10 over n. And I take this limit as n approaches infinity. Again, I make special note to remember, write down limit as n approaches infinity. Okay? Now that we have simplified the problem, we can actually take the limit. As n is going to infinity, think about what 6 over infinity gives us. 6 over infinity is getting closer and closer to the value of 0. Right? So what we now have is 2 minus 0 over, and then notice what happens with this n. 10 over n, 10 over infinity is also approaching the value of 0. So what we have is 1 plus 0. And because I have now, at this step, evaluated, I don't need to write down limit as n goes to infinity anymore. Now I can just simply say what this is equal to. This is now equal to 2 over 1. So I'm approaching the value of 2. Okay? What we say is that it converges to 2. Okay? That's how we say our answer. All right. One more problem just to get the hang of this, okay? So let's go through our 3-step process again. In step 1, divide each term by the highest power of n in the denominator. We'll take a look at the denominator. What's our highest power of n? That's going to be an n squared right there. Okay, so because it's n squared, we're going to take each term, which is 29n, and divide it by our n squared. Okay, oops, that doesn't look like a superscript. Divided by n squared. Okay, and then we add 10 to the 5th power over n squared all over 5n squared divided by n squared. And then we have minus 8 over n squared. What am I missing? Hopefully, you're reminding yourself that, oh, I need to remember to write limit as n goes to infinity. This is a limit problem, not solving an equation. So now we write limit as n goes to infinity, and then we can simplify. What happens with n over n squared? We're going to get 29 over n plus 10 to the 5th over n squared. Notice those are not like terms, right? This is 10 to the 5th. This is n squared. This 10 does not have an n in it. Divided by 5n squared over n squared is 5 minus 8 over n squared. I apologize. Oh, wait, no, I can't. That's the bottom of the page, sorry. And then I need to remember to write limit as n goes to infinity, okay? Now we've simplified everything. We can now do step 3, which is evaluate as n is going to infinity. So as n goes to infinity, what happens to 29 over n? Well, 29 is a pretty small number relative to n, right, which is infinity. So you have a really small number over a really large number. That eventually is going to go to 0. All right, the next term. 10 to the 5th. Oh man, that's 10,000, right? That's a pretty big number. Or 100,000 rather. 100,000 is really big. However, compared to infinity though, 100,000 is actually a pretty small number, right? So you have a small number over a really large number, especially when infinity is getting squared, right? It's getting larger and larger to the power of 2. So therefore, that means that this is also going to the value of 0. So what we have is 0 plus 0 over, and then what we have is 5 minus 8 over n squared. Well, 8 is really, really small, over n, which is infinity, which is really, really large. So that's also going to 0. So you have 5 minus going to 0. And so this is going to end up now, because we have already evaluated our limit, we don't need to say limit anymore. And now we can say that this limit is actually going to 0 over 5 or 0. Because it's going to an actual number, we say it converges as well. And it converges to the value of 0, just like that. Okay? So we're going to stop our lesson here. I know that today's lesson could be very confusing, especially since we're not in class to discuss this together, but hopefully during our Zoom session, it will make more sense as we do more problems together. Okay? All right, well, that's all for today, and I'll see you later this week. Bye-bye.